So on Monday, I said I wanted to look at this function. The function is defined as an integral. But I don't want to do a giant Riemann sum to figure out the value of this integral. And I said we could actually figure out the value of this integral without ever involving any calculus. Let's do this geometrically. Consider the function. Let me call this another y. We're going to call this g of x. And I'm going to call this interior function f of t. Let's graph over here that function f of t. Well, that's just the line y equals x. Let's start evaluating this integral. If I want to know what is g of 1, well, that's defined as the integral from 0 to 1 of t dt. Over here on this picture, what area does that correspond to? Because a definite integral, we're thinking of that as an area. What do I draw? Aha, a line at t equals 1. And then this value is the area here. But wait a second. That's a triangle. And it's not just any triangle. It's a right triangle. Because the t-axis is horizontal, and that's a vertical line. I know the formula for the area of a triangle. It's formula for the area of a triangle. Oh, thanks. Okay. What's the base length on that triangle? What's the height on that triangle? It's also 1, because the graph is y value equals x value. Oh, okay, so wait a minute. This height is 1. I'd like you to calculate for me in this same fashion. G of 2, G of 3, and G of 4. These are all going to be triangles, aren't they? At 2, at 3, at 4. Jack? 2. For each of these, And that means my total area is 2. Now notice we're starting at 0 every time, so it's always a triangle. Not individual rectangles or individual prisms. So I can get all of these. Hang on a second. Let's generalize this pattern. Let's inductively say, hey, look, it works for 1 and 2 and 3 and 4. What about in general? What if I just used an x? Any x value. What if instead of going to 4, I stopped here at that x? Aha! Then the base would be an x, the height would be an x. I'd get a half x squared. Oh, hang on a second. Hang on a second. I now have a formula for g of x that seems to be completely independent of doing an integral. But we defined g of x like that. Okay, hang on a second. I want to ignore the integral for a moment and ask, what is the derivative? What's g prime of x? Aha! It'd be a half times 2x, which would just be an x. Now think of it over here in that integral. That means that I've taken the derivative of this calculation. And I've gotten back x. Now, I remember when we first were talking about definite integrals as areas last Wednesday, we said that the variable in here was really a dummy. It was a placekeeper. So I could think of that integral in terms of any letter I want. So I could think of the integral from a to b of t dt as the same as the integral from a to b of stick person d stick person as the integral of x dx. So this x right here is really playing the same role. I just changed the letter, didn't I? Between Wallace, Newton, Leibniz, Lagrange, Laplace, and a bunch of other mathematicians of the time, they said, wait a minute. The derivative of an area is the thing we were summing up. And thus was born the first version of the fundamental theorem of calculus. The fundamental theorem of calculus, part 1. If f is a continuous function, then the function g of x defined by the integral from a to x of f of t dt, the same way we did that up there a moment ago, is also continuous. What's more, it's differentiable. With g prime of x equal to f of x. If I have any continuous function and I define a function by integrating that thing, the resulting integral is a differentiable function. And the derivative gives me back the integrand. Now, I'm saying this with emphasis and deliberation, and y'all are looking at me like, so what? What this tells me is that taking a derivative undoes what an integral adds up. Integrals added up all these little changes. A derivative measures change. So if an integral adds up all these changes, when I take the derivative, I should get the thing that is changing, and that's the thing that's in here. And I should get it at the end that is changing. Up here, we were changing this right end. So when I took the derivative, I took it here at the right end. And thus this x is our upper end, is what ends up in here. I should be a little more pedantic here and say this is a continuous function on some interval. And then this will be on the same interval. But my derivative may not actually work at each end. That's a rare occurrence. But most of the time, it's sufficient to know that I'm looking at some point in the domain of my function. Why would I do such a thing? This is called a Fresnel function or Fresnel function, depending on whether you want to pronounce the S or not. Fresnel studied optics. There's a reason I wear these stupid cheaters on my eyeballs here. I can see pretty good from about a foot to about 2 meters without them. But you guys, you're all blurry now. And if I try and read my watch, it's a little less than ideal. So I wear these things. But in addition, I got a magnifying glass that I can keep in my pocket. It's made out of plastic. But listen. Do you hear that? Sounds like a zipper. The surface isn't smooth. This is called a Fresnel lens, and it's made by carving very fine grooves into the surface of this piece of plastic. These gather more light by refracting it as if this was a very thick lens, but it's actually very thin. This function measures the angular change needed to create the lens of the appropriate thickness. But that means I need to know where I am from the center of the lens to cut the top of the groove, which means I need to know the derivative of this function, which is exactly a simple calculation. What's the derivative of this thing? I've defined my function in terms of an integral. So when I take the derivative of this thing, I take the integrand itself and replace the variable. That's it. You simply just copy down that integrand, and then you're done. By the way, to my ever immense amusement, I actually got this in the mail. It came with an AARP advertisement. You're old now. Have a magnifying glass so you can see. I keep a lot of stuff about Fresnel with this lens. If I'm taking a derivative, some of my other rules for derivatives apply. Please notice what's important in this integral is that we've defined this as going from a to x. But that also means that I can define other functions. Furthermore, I want the derivative of this. I want g prime. But the x is in the wrong place. Last Wednesday, maybe it was part of Friday, there was a rule that said I could do something with those two numbers, the A and the B. I think it was Friday. What did I do with those two numbers? I really want the X on top. Gesundheit. Sim?
The integral B A to B, what's the next equals integral A to C, effectively that's possible to B.
Okay, so that would allow me to split it up somewhere, right? But I'd still be going from X to C and then from C to 0. So the X would still be on the bottom. In that same vein of properties, further back in the list, If I'm going from A to B, I think of myself as going from left to right. And my delta x's are going that way from left to right. But if I'm going from B to A, I'm going the other way. And that would really mean I want to turn it around. Wouldn't that kind of orient my area? And if going this way gives me a positive number, then going the other way would give me a negative number. So if I want to switch this, I can actually write this from 0 to x, but I get a minus sign in front of it. Then I can take the derivative using the fundamental theorem of calculus. Oh, I like that. I like that a lot. If I have something other than an x, that's an x to the fourth up there. That's not f of x. I'm sorry, g of x. That's g of stuff. Rattle, 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 rattle. What jumps into my head when I hear of stuff? If I want to take the derivative, what's fundamental theorem of calculus tell me to do? I should do that, right? I should just copy down the integrand and change the inside. But what should I change it to? In this version, the integral went from 0 to x. I put the x there. In this version, the integral went from 0 to x, so I put the x there. In this case, the integral goes from 0 to x to the fourth. What should I put there? Okay, so if I put x to the fourth there, my brain says, that's not just an x, that's stuff. And I hear in my crazy infomercial voice, but wait, there's more. Oh, crap. What's supposed to go there? What rule am I invoking when I say that phrase? The chain rule. And the chain rule says you take the derivative of the stuff. And that gets multiplied. Okay, I'll buy that. Questions? So when I take the derivative of an integral, I'm taking the derivative of this added up area And I'm looking at the little bitty change in the area. And that's what a derivative is. So I get the thing I'm adding up pieces of at that end. Now, in this case, it wasn't just going to X, so I have to take into account that extra in between step, that intermediary variable, and that's what our chain rule accounts for. Huh. Questions? Then let me go back to the beginning. We worked out those values based on our picture, right? So here's a question. What if instead of starting at 0, I started at 1? I'm not going to do any calculus. I'm going to do this with geometry again. So let's draw the picture. How do I find the area of that shape? Just geometry, no calculus. I could. I could also use the numbers we already have over here, right? If you think about this number down here, that's the area that goes from 0 to here. That would be including this little extra piece down here. So I take that whole thing, I get 8. If I take this away, I could subtract that part, couldn't I? So I could think of this as the whole triangle from 0 to 4 minus the little bitty triangle that goes from 0 to 1. Hmm. But I know how to get these numbers algebraically. We worked out this function is g of x, right? And we said that g of x was 1/2 x squared, right? I'm going to change the letter because the letter is a dummy. Let's write g of t equals 1/2 t squared. Isn't that the same function? Same exact thing. But this value 8 came from putting 4 in here. And this value 1/2 came from putting 1 in here. So I can think of this evaluation up here as 1/2 4 squared minus 1/2 1 squared. That's going to give me the same number, 7.5. The first number is 8, the second number is 1/2. Subtract, I get 7.5. How does this function relate to that function? Now I need to go back to chapter 4. to the very last thing we did on the exam. Jack, you just nodded. What'd you hear in the back of your head? The antiderivative. It's not the antiderivative, it's an antiderivative, right? Because I could have any sort of plus C on there if I wanted to, but it's an antiderivative. So you're telling me that when I want to do this, I take the antiderivative, I plug in, right? That little vertical mark, we wrote dy dx, and we said plug in, and then we put an x value. And then I do the same thing at 1. So just like our derivative of an integral canceled the integral out, our derivative is undoing an integral. That means an antiderivative does an integral. Here is the second part of the fundamental theorem of calculus. If I have a function that is continuous on some interval, then the integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F prime is little f. In other words, f is any antiderivative for little f. Holy crap, if I know how to do antiderivatives, I know how to do integrals. Whoa. Any function where I know how to take the antiderivative. When we did this problem on Friday last week, it took us 30 minutes because we had to do all the rectangles and we had to do all the sums and we had to do all the adding up, and it was a pain in the ass, and it took half an hour. Ready? What is the antiderivative of x cubed? What is the antiderivative of 6x? Because it's x squared over 2, there's a 6 out front. Now I could put a plus c, right? If I want to do an antiderivative, I could put any c I want. I'm going to pick c equals 0. I'm allowed, it says, any antiderivative. To show you why, I'm actually going to put the plus c. And I'm going to plug in these two numbers. Plug in 3, plug in 0. 1/4 of 81 minus 3 times 3 squared is 9, plus c, minus 1/4 of 0 minus 0 plus c. What happens to my c's? Grab your calculators. What's 81 over 4 minus 27? That took us 30 freaking minutes on Friday. It took me a minute and a half today. If I can do antiderivatives, I can do integrals without ever doing another Riemann sum. I told you there had to be a shortcut somewhere. This is that shortcut. Provided I know the antiderivative in question. What's the antiderivative? 1 over x dx. This is my special case. This is the ln. ln of the absolute value of x. Now, I'm going to shortcut this notation. Instead of writing this twice, I'm going to write it once. 1 bar. And if we think of the top and the bottom, I'm going to put the top number at the top, the bottom number at the bottom. That's just a shorthand for saying you should plug in the top number first and the bottom number second and subtract. So instead of having to write my antiderivative twice, I can just write my antiderivative once. And if you work this out, you get 0.693147, et cetera, et cetera. ln of 6 minus ln of 3. As long as you know the antiderivative in question. The problem this makes is that I have to pattern match. I have to say to myself, do I recognize this as the derivative of something? 1 over x I recognized as the derivative of ln of x. X cubed and 6x I could use the power rule on. Those are polynomials. I know how to do the power rule there. Trig functions, I'll need to recognize, oh, right, the derivative of tangent is secant squared. So if I see an integral with a secant squared in it, I should be thinking about that. Fortunately, I have a formula sheet with all of those. This is also on that formula sheet. Dean? This is the inverse tangent. But without that recognition, this might as well have been written in Greek. Inverse tangent of pi over 4 is 1. Inverse tangent of 0 is 0. There's an inverse tangent button on my calculator. The following is wrong, and I want you to help me understand why. That is 100% wrong. Huh. The antiderivative of 1 over x is the ln of the absolute value of x. I put in 1, the absolute value of 1 is 1. Put in -1, the absolute value of -1 is 1. So I get ln of 1 minus ln of 1. That's right. It's this step that's wrong. Why is going from here to here wrong? That's what I'm using, right? The fundamental theorem of calculus. Why can't I do that here? Where is this function undefined? And 0 is right in the middle of that, isn't it? Ah, crap. The reason I'm not allowed to do this is because the function I'm looking at is not continuous. I'm only allowed to use the fundamental theorem of calculus when my function is continuous. Or where the discontinuities are removable. Remember, we talked about differences between the types of discontinuities. We had holes, we had jumps, we had gaps. This one's got an asymptote in it. Can't do that. If it's just a hole, then I might be able to work around it. I'm going to save that for a later course. We'll talk about that in the theory side in SMA 207. But for the moment, I can just say, hey, it needs to be continuous. This one ain't. This is amazingly powerful because what was an absolutely crazily difficult bothering of adding up all of these rectangles blew up. Took half an hour. Nope, not anymore. All I have to do is know how to take an antiderivative. So there are two main goals remaining in all of calculus. First is to look at a function and decide, does this have an antiderivative that I can figure out? Because if it has an antiderivative, then I can do all these integrals. But the second is to recognize the situations where an integral is useful. Why integrate? What benefit is there to finding the area under a curve? To doing these sorts of summations? What good are they? In a very real sense, the entire rest of Calc 1 and almost all of Calc 2 is related to this question. Why am I going to bother? I'm not going to answer that in 2.5 minutes, so I think I'm going to stop here today. I will leave you with a parting note, quite literally. A number of years ago, I was at a conference and there was a performance of a musical. And this musical contained all sorts of math jokes. One of my favorites is a song about Riemann integrals, about doing Riemann sums, which of course is to the tune of M&Ms without me.
GFB, Riemann, no gimmicks.
To find the whole area under the curve, under the curve, under the curve.
I can't do this section without hearing this thing in my head.
The whole area under the.
Anyhow, I put the poster on our Canvas page if you're interested. It's very silly. I will see you all. Have a wonderful rest of your day.